Hey guys, this is video number one. I'm going to start by recapping the activity that we did in class on Wednesday, just as a refresher, because it's probably been a while. Last time I saw you, we looked at the question of whether it matters where students sit in the room. In other words, students that sit in the front of the room get better grades than students that choose to sit in the back. And I had a set of data for you from a couple years ago, and we looked at, or made a scatter plot rather, of students' seat locations compared to their exam scores. And when we did the least squared regression line, we had a slope of negative 1.517. So not a really strong negative linear association, but there still was a negative slope there. And so what we were really interested in is determining whether this was a relationship that just happened by chance, or if there was convincing evidence that seat location did have an effect on grades. So we ran a simulation under the assumption that seat location had no effect on exam score. And if that was true, we should be able to just take all 30 scores, randomly assign them to different rows in the room, and calculate the slope. And we would probably get negative slopes in most cases if the seat location did make a difference. So when we looked at the results that you guys got from your simulations, some of you actually got a positive slope, some of you got a negative slope. And so we sort of had mixed results. So what we did there is we ended up running a simulation on the applet. And from the simulation, we did 1,000 trials. And when you look at the results of those simulations, you will notice that we actually had quite a few that were very close to zero, right? And a slope of zero would indicate no relationship between seat location and grade. All of these results over here actually had a positive slope, meaning that students that sat in the back of the room would actually score better. And then we had a bunch that were negative. So sort of a mixed bag. And in the end, what we ended up looking at was what would be a potential p-value. And our p-value would be the number of simulation results that were at the result we had from my class, which was negative 1.57, or more extreme than that. And we had 128 dots, or 12.8%, that would sort of represent our p-value. So if our assumption that we started with was that there is no relationship between seat assignment and location in the room, a p-value of 12.8% would mean we would fail to reject that hypothesis. So we don't have convincing evidence that seat location makes a difference. Now, the important ideas in this section are kind of relating a statistic from a sample to a parameter. And we've been doing this all semester with different types of confidence intervals and hypothesis tests. And now we're going to do this for slope and linear regression. So as a recap, we're just going to kind of talk about some symbols that we use when we're dealing with linear regression. We, in the past, like when we did chapter 3, we used the symbol B to represent the slope of a best fit line. We used A to represent the y-intercept. And so when we wrote the equation for the least squared regression line, we wrote it as y hat equals A plus bx. We talked about the standard deviation of the residuals, which in chapter 3, we use the symbol S. And we also talked about the standard deviation of the slope, which would be the standard error, and then so SE sub B. Now, with a parameter, what we're talking about is a true value of a slope for a population instead of just a statistic that we get from a sample. So in our seed example, it would be, for example, if we had all possible students and we plotted their seat location versus their exam score, what would be the slope of that least squared regression line? And so the parameter we would use there would be beta. For the y-intercept, we would use alpha. And then the equation for the least squared regression line would look like this. So we would use mu sub y, and that would be alpha plus beta times x. The standard deviation of the residuals, we'll use sigma, and the standard deviation of the slope, we'll use sigma sub b. The symbols aren't really that important in this chapter. We won't really use them a ton, but I just kind of wanted to point out the difference between a statistic and a parameter, just like we've done in the past with p hat for a statistic and p for a parameter, or x bar for a statistic and mu for the parameter. We're looking at now an example where we collected some data using helicopters. So a few years ago, we made some paper helicopters. We made 70 of them, in fact. We dropped 14 helicopters, each from 5 different drop heights, which are 152, 203, 254, 307, and 442 centimeters. So at those different drop heights, then what we did is timed how long it took for the helicopters to float down to the ground. And then we performed a regression analysis on that using some computer software. So just as a reminder, in case you've forgotten how to read these, they kind of give you an indication up here of what your variables are. So we have flight time and drop height. They will tell you in the table one of the variables, and they'll always give you the explanatory variable, which is x. Now, in the column that's labeled coefficient, there are 2 numbers underneath there. The first number that they give you where it says constant, that's A, and that's your y-intercept. The number that's next to your explanatory variable then will be B, which will be your slope. We've used S before. That's the standard deviation of the residuals. And of course, we've used R squared. In the second column, we really haven't used these yet. So where it says SE, that's standard error of the coefficient. So in the first row here, this would be the standard error of your y-intercept. So that's SE sub A. Sorry, that's a little bit messy. And this second number here would be the standard error of your slopes. And the other columns for now we're not going to use, so don't worry about those. So first, from the regression printout, what's the equation for the least squared regression line? It would be predicted flight time equals negative 0.03761 plus 0.0057244 times the height. And that would be the drop height for the helicopter. Part B asks, what if, suppose a helicopter is dropped from a height of 442 centimeters and had a flight time of 2.2 seconds. What is the residual? Okay, this is again review from chapter 3. So what we need to do is calculate the predicted flight time. We do that by plugging the drop height of 442 centimeters into the equation. That gives us a predicted flight time of 2.49 seconds. The residual, you may remember, is the observed minus the predicted value. And the observed was 2.2 seconds. The predicted was 2.49. So that gives us a negative residual, negative 0.29 seconds. So that stuff is all kind of review from chapter 3. Now, part C says, what is the estimate for beta sub naught? Now, this is, I apologize for this. This is actually like an updated symbol thing that I forgot to change in your note packets. I was kind of in a hurry to print them off for you last week. So cross this out. This actually should be alpha. Okay, they've kind of updated those symbols. So this is asking us, what is an estimate for the true y-intercept for the population? And we can use our sample y-estimate to get an estimate for the population parameter. So that would be 0.03761. And if we would interpret that, we would say, if the helicopter was dropped from a height of 0 centimeters, then the flight time is predicted to be that's negative 0.03761 seconds. Sorry, I missed that negative sign there when I wrote the alpha symbol in there. Now, part D says, what is the estimate for beta sub 1? Ignore that subscript there. Okay, really what they're asking us for is the estimate for beta, and that's the estimate for the population slope. Well, we can estimate the population slope by using the sample slope, and that is 0.0057244. By the way, I did mention up above that y-intercept there being negative really doesn't have any meaning in this context, because if you have a helicopter at a height of 0, you're not going to have any drop time whatsoever because it's already on the ground, and it's certainly not going to be negative. Anyway, back to interpreting the slope. If our slope is 0.0057244, we would interpret that by saying, if the drop height is increased by 1 centimeter, then the flight time is predicted to increase by 0.0057244 seconds. And that interpretation is kind of review from chapter 3 as well. We did a lot with interpreting slope and y-intercept. Now E says, what is an estimate for sigma? And that would be the standard deviation. So that's 0.168181. The interpretation of that is that the actual flight times will typically vary by 0.168181 seconds from the times predicted by the least squared regression line. So that's sort of telling us if we went through all of the flight times and we predicted all of those using the least squared regression line and the drop heights that we were given, how far off would we typically be? Now, F says, get the standard error of the slope. And that says standard error of B, and we're just cross out that one again. We don't need that little subscript there. And how we would interpret that is that if we repeated the random assignment many times, by the way, that standard error was 0.0002018. If we repeated the random assignment many times, the slope of the sample least squared regression line typically varies by that big long decimal from the true slope. Okay, so this might be a little easier to think of in context of our seating example. Remember what we did is we took everybody's scores and we randomly assigned them to seats. And we can repeat that process many, many times. And so what this is telling us is then if we did that process with the helicopters many, many times, the slope of the sample least squared regression line that we get, how much that would vary from the true slope. All right, that is the end of video number 1. You actually don't need to do this 12-1 worksheet because we're going to do all the assignments in class when we get back from spring break and from the end of testing week. So thank you for watching video number 1.